Alright guys, here's your helpful hint video for this week's FRQs. We're going to be starting off with the one that is on page 134. A lot of this I would think you guys probably are going to be okay with. I'll just kind of point you in the right direction. Not necessarily going to do the whole thing for you. If you want to see it worked out, you can look at the videos on YouTube on how to do it. But this is just to point you in the right direction. Alright, so let's read it here. Traffic flow is defined as the rate which cars pass through an intersection, measured in cars per minute. The traffic flow at a particular intersection is modeled by this function. So that means that F is measured in cars per minute. This is a rate. I want you guys to understand that. This is telling you how quickly cars are moving through the intersection. So for instance, if you guys plugged in f of 3, for instance, whatever you get for that, that would represent how many cars are moving through the intersection per minute at that point in time. So this is a rate. So the units would be in cars per minute. And it just basically tells you how quickly the cars are moving through the intersection. Now in part A, they're asking you to find not how many cars pass through the intersection per minute, just how many cars actually pass through the intersection over a 30-minute period. Well, in class we've learned that to turn a rate, which is cars per minute, into a y value, you integrate that rate, and that will eliminate the time factor, and that will give you an answer for cars. So I'll let you guys do that. Now for the next one, is the traffic flow increasing or decreasing? Now they're asking here about, is this function increasing or decreasing? So what you would need to do is you would need to find out what f prime of 7 is. And the question is it greater than 0 or less than 0? Okay? If it's greater than 0, then the traffic flow is increasing. If it's less than 0, then the traffic flow is decreasing. And once again, you can just plug this right into your calculator. You don't need to do any calculations by hand there. Part C, average value of the traffic flow. So this is the traffic flow. I want to find the average value of that function. So if I am finding the average value of this function over the interval from 15 to 10, this would be your setup here. And that's going to give you the average value. Now the units on this are a little bit tricky though. Now we've already talked about this. When you integrate the f function, it goes from being cars per minute to just cars, right? However, we're multiplying it by this, and both of this 15 and the 10, those are time units. So now we have 1 over 5 minutes. So now we're back once again to cars per minute. So your units will go back to being cars per minute. And that makes sense. If you're trying to find the average value of this function, then the average value of that function should have the same units as the original one. So even though when you integrate you lose a time factor, since we're multiplying it by a time factor, we get that time factor back and we end up with cars per minute. The last one here is asking you guys to find the average rate of change of the traffic flow. So how quickly is this thing changing on the interval from 10 to 15? So that's f of 15 minus f of 10. This is the average rate of change. Now you got to watch your units though, right? On the top we have f, and f is cars per minute. But on the bottom, what do we have? We have minutes. So we have cars per minute, in other words, cars per minute squared. So be aware of that. Okay? Alright, let's go ahead and move on to the next question. So this problem here, which can be found on page 156 of your blue books, is our second one. And this one throws us for a little bit of a loop, and it's because the time intervals don't match for our rate ins and rate outs. Let's go ahead and read it and see what we mean by this. When a certain grocery store opens, it has 50 pounds of bananas. That sounds like a starting amount to me. Customers remove bananas from the display at a rate modeled by this. So this is how quickly they are removing the bananas, and that's measured in pounds per hour. So for instance, if you were to plug in 1, that would tell you how many, at that point, f of 1 would tell you at what rate, how quickly are customers removing the bananas at that point in time. The next one here is after the store has been open for 3 hours, the store employees start to add bananas. So we have a rate out, and this is our rate in. We have bananas leaving, we have bananas being added, but notice it's after 3 hours, so this interval starts at 3. So for the first 3 hours, all we have is this function up here, removing bananas, and then after that, we have bananas going out and coming in simultaneously. So we're going to have to treat those two pieces differently. We can't just put them together unless they're on the same interval. So in other words, we could put these two functions together for 3 to 12 because they both go from 3 to 12. But for 0 to 3, we can only use this guy because that's the only one that exists at that point. And once again, I overlooked this, but the units for the rate in is also pounds per hour. So question 1, how many pounds of bananas are removed from the display hour for the first 2 hours? Now, if we're only looking at the first 2 hours, then we only are concerned with this function. And besides, they're asking about being removed anyway. So that would be from 0 to 2 for f of t, right? Now for the next one, f prime of 7. This is interesting. What does this mean? Well, already f is in pounds per hour, right? So if you're finding the derivative of f, you're finding how fast that's changing. So basically what you're going to do is you're going to calculate the derivative of f, and it's going to end up being, well, you know what, tell you what, I'll just do this one because it's a little bit, we haven't done something like this in a little while. So let me bring up my calculator. I'll show you guys how you can do this. All right, so let's go ahead and put the f function in there. It's 10 plus 0.8 t sine of t cubed. That didn't type right. Divided by 100. Oh, not 10, 100. All right, I think we got that typed in correctly. Okay. So now we're going to go back to the home screen here, and I want to find the derivative of that thing at 7. So we go to Math, and then we're going to go to 8. Now you might have the good-looking calculator. I have the ugly one. So I'm going to put my function in first, comma x, comma, and then what number I'm trying to find the derivative at. And I'm getting negative 8.1195, etc. Now, just so you guys know, you always want to make sure, go to mode. You want to make sure that your calculator is in radians, because if they accidentally get set to degrees, you're going to get wrong answers. So always make sure your calculators are set to radians. But anyway, we have that as our answer there. If we round to the nearest thousandths, it would look like that. But what are the units? The units are, well, the units of f are bananas per hour, right? Or pounds, I guess we should say pounds per hour, right? But when you take the derivative of that, that's pounds per hour per hour. In other words, pounds per hour squared. So, now they want us to interpret what that means in the context of the problem. So, we need, remember with interpretations, we need 3 things. We've gone over this a lot. We need input units. We need output units. And we need the context. So, here's what this means. This means that the rate at which bananas, the rate at which bananas are being removed is negative. So the F here represents the rate at which bananas are being removed from the display shelf, right? So this thing here represents how quickly that rate is changing. So that rate is decreasing at a rate of 8.120 pounds per hour squared. So here's how we would write our answer for number 7. At t equals 7, and that's hours, there's my input units. At t equals 7 hours, the rate at which bananas are being removed there's my context. The rate at which bananas are being removed is decreasing at a rate of 8.120. Notice I'm not going to put negative on there because I said it was decreasing. That implies that it's negative. If you put a negative, that's like a double negative. And we don't want to forget our output units now. 8.120 pounds per hour squared. Okay, and there's my output unit. So at t equals 7 hours, the rate at which the bananas are being removed is decreasing at a rate of 8.120 pounds per hour squared. Okay, for part C, is the number of pounds of bananas on the display table increasing or decreasing at time t equals 5? So let's go ahead and see if we can figure that out. So we know how quickly the bananas are being added. That's by G, right? There's the rate at which they're being added is G. And the rate at which they are being removed is this other one up here, which is F. See if it gets to line up again here. All right. So we're gaining bananas at this rate, and we're losing bananas at this rate, and they want to know what's going on at 5. So if we plug in 5, the question is, what do we get? Do we end up with a positive number or a negative number? Positive would mean increasing, negative would mean decreasing. All right, let's take a look at part D. How many pounds of bananas are on display at the time t equals 8? Now, this is going to be a little bit different than what we've usually been doing in class. And the reason it's going to be a little bit different is because these functions operate on different intervals. So usually in class, what we've been doing that's kind of relevant to this is, well, first of all, let's make up a new variable. We're going to call it b of t to represent the pounds of bananas at time t. So I'm creating a new variable. So I'm going to define it before I begin. Now, don't write this down because it's going to be a little bit different. But what we've been learning in class is that we've been learning that the final amount is equal to the starting amounts, whatever your starting time may be. In this case, we're going to go with 0, plus the integral from 0 to whatever time you're looking at for your rate in minus your rate out. But there's a little bit of a problem here, and the reason we have a problem is because for this particular question, both functions do not go from 0 to t. One of them does, the other one does not. Let's go back up and take a look at the top here. Notice that the f function does go from 0 to 12, but the g function only goes from 3 to 12. So for some interval of time, specifically for the interval of time from 0 to 3, bananas are only being taken away. There's no gain. So that's a little bit different in how you're going to have to calculate things. Okay, so let's go ahead and slow down here a little bit. They're asking how many pounds of bananas are on the display table at time t equals 8. So we would say that the number of pounds of bananas, represented by b of 8, is equal to the starting amount plus the number of bananas that have been removed on the interval from 0 to 3. Because remember, from 0 to 3, they're only being removed. There's no g function in this integral because the g function doesn't start until after the 3rd hour. So this is the number of bananas that are on the shelf already, and this is the number of bananas that are being removed. So actually, I should have put a minus because we are losing those bananas, right? This represents how many pounds of bananas will be lost on that first 3 hours. So we have our starting amount of bananas. Then we have this amount here, which represents that which was lost in the first 3 hours. Now on your FRQ, you wouldn't need to write these things that I'm writing here, but I'm just explaining things. Then after that, we start gaining bananas again, but we're losing them at the same time. So from the 3rd hour all the way up until the 8th hour, we are gaining bananas with the function of g of t, but we're also losing them at the same time. So we have our rate in, rate out there. So you're going to calculate this. So this is a little bit different from what we had in class because our intervals don't match. This guy is kind of like the new piece that we have to throw in because it exists all by itself for part of the time interval that we care about. So there you have it. I'll let you guys take it on from there. Just going to move to our next one. Okay, now as for this one, which is on page 118, a lot of these questions are pretty straightforward. Not a whole lot of tricky stuff, except for maybe part B is a little wild. But let's go ahead and take a look at it. So for part A, you guys know how to do this already. We've done this in class. How do you find the place where it's farthest to the left? That's the candidates test. Candidates test. So there's that. The other difference is that for the problems that we did in class, you guys had to calculate the areas using geometry, but on your problem here, they're telling you the areas are -8, 3, and -2. So you don't have to. It's actually easier. It's less work. So I'll leave you guys do A. Parts C and D. Well, we'll get to that in a minute. Let's talk about B. So as for B here, B says for how many values of t on the interval from 0 to 6 is the particle at x equals -8? Explain your reasoning. So what's going to come in handy here is you need to have your answer for part A to answer this question. But I'll tell you this much. It's an intermediate value theorem question. So I'll kind of refresh your minds on what that means. So basically, you're going to be looking at your candidates test, right? You're going to have some numbers over here, and then you're going to have some numbers over here. And the question might be something like, you know, in this case they're asking how often is it -8. I'm going to say how often is this thing equal to 5. Okay, well, if this is a continuous function, which it is, and we'll talk about how I know that is in a minute, but if this is a continuous function and I'm going from 3 to 10, then at some point I had to cross 5. So there's once. And then if I'm going from 10 to 4, I would have to cross 5 again. Now if I'm going from 4 to 1, not there. You don't have to necessarily cross 5 in order to get to 4 to 1. You could, but you don't have to. So for mine, I would say there's at least 2 places where y would equal 5. So twice. Now my reasoning would look like this. This is how you explain it. You would say, since y is continuous on the interval, I guess I better put some numbers over here so I can use intervals. on the interval from 1 to 2, and goes from 3 to 10, there must be some value x such that y of x equals 5. Okay, it's just a fancy way of saying if I'm going from 3 to 10, I have to cross 5 at some point in that interval. I would have to say this again for the next time. So you have to say it for every time it crosses the value they're asking about. So the last thing I'll add to you guys for this question is, how do I know that it is continuous? Well, the problem that we're looking at is, let's see, what's it asking? How many has it x equals 8? Well, they want to know how many times does x equal 8. Now, x is an integral function of the velocity function, right? Now, the derivative of x, therefore, this would cancel out, and we'd be just left with v of t. So the derivative of my position is velocity. Now, look at my velocity graph. It's continuous. There are no holes, gaps, or jumps. And if a function is, if a function has a continuous derivative, that means it's differentiable. And it says it right here anyway, so I guess I didn't need to go through all that. But so the point is that if a function is differentiable, it has to be continuous also. So since v of t is continuous, x of t is continuous as well, and that means we can use that theorem, which is the intermediate value theorem. So I'll let you guys handle it from there. Let's go ahead and say, now for C and D, I don't think I need to give you guys any helpful hints. Those are both very direct questions. We did things explicitly like that in class. So I'm going to go ahead and let you guys hit those up on your own. And that's that.